Hello, Chem 44 students. This is Professor Medyo Anagila, and in this video, we're going to have some practice problems on alcohols. So please have some pens, papers, so we can follow along with our practice problems. So problem 1, draw the structures of the following alcohols. 1,2-diphenyl ethanol and 3-methyl 3-hexene 2-ol. So for the first one, since we're looking into the main carbon chain, it's referred to as ethanol, so that's a two carbon atom, and then we have diphenyl. When we have diphenyl, that's actually a substituent, which is the aromatic ring, and it is on the 1,2 positions for the carbons in ethanol. So that means this is position 1, so there's an aromatic group there, and then this is position 2. There's also aromatic group there. For the second one, we have 3-methyl 3-hexene 2-ol. So what we can do is we can also draw out the longest carbon chain. So it is hex, so 6 carbon in, so there's an alkene there at position 3, and there's an alcohol at the position 2. So if we draw that, so this is the 6 carbon chain. If we start off our numbering from here, so that means the alcohol would be in this position since it is 2-ol, and 3 position would be for the alkene. So you will start off at carbon 3, okay, and then you have 3-methyl on the third carbon as well. So this is the structure of the 3-methyl 3-hexene 2-ol. I hope we got these two correct. Now, moving on to the next set of problem. This case, we are asked to give the IUPAC name of the following alcohols. So we have 2 examples here, giving you some time to try to work it out. Okay, so let's try to name the first one. So if we're going to name the first one, we see that there's an ether group and there's the alcohol group. Now, in terms of hierarchy, the alcohol has the higher hierarchy than that of the ether group. So we can name it as a substituent. The ether group can be named as a substituent, and the parent can be should be the alcohol group. Now, this alcohol, so as an alcohol group, we can actually have it as a 1-carbon alcohol, which is methanol, and the methanol has this whole thing as a substituent, which is a phenyl group. This is a phenyl group, but it is substituted with OCH3. So if we're going to name that, so we have phenyl, and then the substituent on the phenyl is methoxy. And it is at 1, 2, 3, 4 position. So we have 4-methoxyphenyl methanol. We can also name this as naming it as this alcohol, the one with the blue rectangle. So that blue rectangle is actually a benzyl alcohol, so wrong spelling. And it will be as a substituted benzyl alcohol at the 4 position, or we can also refer to it as the para position. So this would be para-methoxybenzyl alcohol. For the second example, we need to figure out the longest carbon chain length with the alcohol as its main functionality. So this is the alcohol, OH. So from that position, we have 1, 2, 3. We can go about going to the left and to the right, but definitely we're no longer going to be moving up right because that's just a methyl. But if we go down, okay, so we should go down here, okay, we see that it becomes, or it has more or a longer chain length. But the question now is, are we going to the left or to the right? If we go to the left, the alkene will be part of the main chain. But if we go to the right, the alkene will just be a substituent. And because of that, we'll be opting to go to the left so as the alkene will be part of the main chain. So 5, 6. So this will become a 6 carbon but with an alkene in it, rather than a 6 carbon with the alkene as the substituent. So the main carbon chain length would be named as, since this is a 6 carbon, it will be named as hex, and then the parent functionality would be the alcohol, but the alkene is part of the main chain and it start off at position 4, so 4N, and then position 1 for the alcohol, 1 all. Okay. And then now, we have substituents methyl and ethyl at position 3 and 4. But since this is ethyl goes first in terms of alphabetization, okay, so we're going to name it first. So for ethyl, 3 methyl, hex 4 and 1 all. Another thing that we might not have realized is that there's a certain stereochemistry for alkenes, right? So in this case, this is not cis and trans because there's 3 different groups, not just hydrogen on the carbon involved in the double bond. But rather now we're going to prioritize the group per side. So in this case, if we go the left portion, the priority would be the one on the top. And then if we go on the right portion, the priority would be the one on the top as well, because this group has the alcohol on it. This group has only ethyl on it. So that the priority 1, 1 are on the both side. So this would be the Z stereoisomer. So the complete name is Z 4 ethyl 3 methyl hex 4 and 1 all. So I hope we realize the complete name. Okay, so let's move on to problem 3. For problem 3, basically, we're just going to provide some chemical tests and what do we expect from it that can differentiate these 2 pairs of alcohols. And among the chemical tests that we have, the best way that actually we can differentiate this out is via the use of the Lucas test, which is the concentrated HCl with zinc chloride as the reagent, and then the Jones reagent or the Jones test, which is basically acidic chromium trioxide. And depending on the alcohol, we have primary, tertiary, secondary, tertiary. So for the Lucas test, primary, normal conditions without really prolonged heating, it's negative. That means when we say negative, so the positive result for the Lucas test is turbidity. And we just need to somewhat quantify if it is fast or slow, or totally no formation of 2 layers. For Jones test, basically this is the positive test is, the positive result is the formation of opaque, greenish to bluish, blue-green or bluish-green mixture coming from oranges. Okay. So primary alcohol will not result to any turbidity even at prolonged time. Okay. So, secondary alcohol under Lucas test would be positive, but the turbidity might occur between 2 to 5 minutes. And for tertiary, this is positive, but it's quite fast, even less than 1 minute. So that's the differentiation of the types of alcohol in the Lucas test. But for Jones test, since this is an oxidation process, so positive on primary and secondary, now negative for tertiary. So to make sense of the chemical test, you should be citing both tests, and the combination of it will give you a better way to differentiate primary, secondary, and tertiary. And with this, we're going to differentiate 2-methyl-2-propanol with that of 2-butanol. Of course, to guide us, we need to check the structure first. So 2-methyl, 2-propanol with methyl at the second position and OH also on the second carbon. Versus 2-butanol, 1, 2, 3, 4. So, second position. So, how would we differentiate these two out? The 2-methyl-2-propanol is a tertiary alcohol, while the 2-butanol is a secondary alcohol. So, obviously, if we check the combination of Lucas and Jones test, the 2-methyl-2-butanol should be having a fast turbidity upon Lucas test but negative on the Jones test. The 2-butanol should have turbidity within 2 to 5 minutes under the Lucas test and positive under Jones test. Okay, so that's how you're going to differentiate these two. And for 1-octanol and 2-octanol, obviously 5, 6, 7, 8. This is 1-octanol. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. This is 2-octanol. For these two, so we're going to have Lucas test for 1-octanol is negative, so it will not result to turbidity even under prolonged time, but positive on the Jones test, formation of opaque green-blue mixture. 2-octanol, same results with Jones test, formation of opaque green-blue mixture, but it will be positive in the Lucas test at about 2 to 5 minutes. So that's how you're going to differentiate it. Now, you might ask, can you use pyridinium chlorochromate lumindol. Pyridinium chlorochromate, I encourage you to really take note of the name of the reagents rather than the actual reagents, the actual chemicals in the reagent rather than the acronyms of it. So pyridinium chlorochromate Chloro. There's an O there. Can you use this to differentiate 1-octanol from 2-octanol? We've learned that if you use pyridinium chlorochromate, primary alcohol will not be oxidized to the carboxylic acid, but rather it will stop at the aldehyde. But this is still a chromium-based oxidizing agent. It will still react with secondary alcohol, and it will oxidize the secondary alcohol to ketone. So that means both of this, 1-octanol and 2-octanol, will give you or will give a positive result with PCC. So it will not have a very different differentiation from the Jones test. So you still need to make use of the Lucas test. So the combination with the Lucas test. So moving on with problem 4. For problem 4 now, we're asked to give a synthetic scheme for the synthesis of these alcohols. So let's work on first on the left side. What we know from here is that it gets converted from an alkyl halide to a halohydrine, or to be specific, a bromohydrine. What we learn is that we can generate the bromohydrine from the alkene. So that means we should convert first the alkyl halide to an alkene, and then most likely the alkene version that will give the bromohydrine here is the cyclohexene, and the reagents to give the bromohydrine is bromine with water. Now, to convert cyclohexyl chloride, so we need to do an elimination. So we need to have a base with heating. So you can use KOH in ethanol. Okay. Sorry about that. So let's write the whole thing. KOH, potassium hydroxide in ethanol, to give you the cyclohexene. So that would be a synthetic scheme for the synthesis of the alcohol given, provided what we know at this point. Next, what we see here is it gets converted to a primary 1, 2, 3, 4, 5, 6. So 1 hexanol to 1, 2, 3, 4, 5, 6. 2 hexanol. Primary alcohol to a secondary alcohol. Okay. So from what we know so far, the best way to get to the alcohol, based on what we know so far, is with, of course, from alkenes. So we can generate the alkene from, or rather we can convert the given reactant to an alkene. And since this is a primary alcohol, what we can do is have it do elimination using POCl with pyridine. And generally, this is also being done at low temperature. This is actually the beauty of this reagent. It can be done at low temperature. And you'll be having 1-hexene. And then from 1-hexene to give the 2-hexanol, this should be a Markovnikov reaction. So among those that we learn, the oxymercuration, demercuration can give us the Markovnikov product. So 2 sets of reagent. The first one is mercuric acetate with water. Sometimes there's also tetrahydrofuran as the solvent. And the second one would be the reduction with sodium borohydride. So this would be our proposed synthetic scheme to convert 1-hexanol to 2-hexanol. For our next set of problem, give the major organic product, if any, of the following reactions of 1-butanol with the following reagents. So just give the major organic product. So this is 1-butanol. Reacting it with a strong base, what will happen is it will get deprotonated and will get to the 1-butoxide. I was just trying to draw the lone pairs. B is an oxidation. So this is a rather strong oxidant. So it will be converted to the carboxylic acid. So instead of an aldehyde, it will be converted to carboxylic acid. There you go. Letter C, this is pyridinium chlorochromate. So this is the milder oxidation. So now, the oxidation will stop at the aldehyde. Reacting 1-butanol with concentrated sulfuric acid and with heat, so this will favor dehydration or elimination. So you'll get to the 1-butene via an E2 mechanism. Now, if you subject it to concentrated hydrochloric acid with zinc chloride, this is via an SN1 mechanism. This is the primary alcohol, so there's no reaction that will occur. So you can just write NR, meaning no reaction. So as a primary alcohol, it will not react with the given set of reagent. This is actually the Lucas test. Now, lastly, with thionyl chloride, PY here is pyridine. This is introduction of the Cl group to primary or secondary alcohol via an SN2 mechanism. But since there's no stereocenter in the alpha carbon, so we're not actually particular about it. But if this is a very specific, there's a stereocenter on the alpha carbon, so we have to take note of the mechanism. This is an SN2, so that means there's an inversion of the stereocenter. But for this case, that's not a factor, but we're converting OH to, or we're substituting OH to a Cl. So it will become a 1-chlorobutane. Okay, so these are the major products as applicable when 1-butanol reacts with the given set of reagents. Problem 6 asks us to provide the structure of the compounds A and B. These are actually isomers of one another of the molecular formula C5H10O2 with the following information. So we have, for compound A, given the information, we have IR, carbon 13, and the spectrum for proton, and some chemical tests. For B, also the same set of characterization, chemical test, IR, carbon 13, and the given spectrum for the proton NMR. If you are given such problem, the first thing that you need to consider is to determine the degree of unsaturation. So the degree of unsaturation has the formula rho, or whatever formula or symbol that you used before. So this is 2 plus 2 carbon plus nitrogen minus H minus X all over 2. So for this problem, this would be 2 plus 2 times 5 for the carbon minus 10 for the hydrogen divided by 2, and then this will give us 2 over 2. This will cancel out. So 1. What does a degree of unsaturation 1 mean? It has a double bond or a ring. There's 2 oxygen in the molecular formula, and as an additional clue that I will give to you, this peak actually in the IR spectrum refers to C double bond O. Okay, so automatic, there's a carbonyl. This is a carbonyl group. Okay, so it is in fact a ketone. So that's another clue that I will give to you. So it is a ketone. So one of the oxygen is already accounted for. So we're on the topic of alcohol, so naturally we should be expecting that the other oxygen in the formula would be for an OH. But to check that, compare the IR. So the OH for the IR is within the range of 3200 to 3400, depending on if it is a free OH or hydrogen bonded. So this actually, the presence of 3300 to 3200 reciprocal centimeter or wave number in the IR spectrum refers to the OH group already. Okay. Now, comparison of the Jones test and the Lucas test. positive on the Jones for A, negative on the Lucas. So that combination actually give us primary alcohol. But for B, positive on the Jones, positive on the Lucas, but a little bit slow. So this give us a secondary alcohol. Okay. Another information that we need to take note would be the carbon 13 and the proton NMR. So we know that the alpha carbon for an alcohol is within the range of 50 to 80 ppm. So what we have here, so this one might fall under the 50 to 80. Actually, it falls in the range of 50 to 80. So this will signifies the possibility of that alpha carbon, the one that bears the OH. For our additional knowledge, the 210 here refers to the C double bond O carbon. So it really appears at quite a high ppm because it's bonded to an electronegative atom and it's double bonded. So, and then all the rest are more likely an alkyl. Okay. One thing that you should take note for NMR, the number of peaks. So for carbon, for A, we have 5 for carbon. For proton, we have 1, 2, 3, 4, 5. 5 also for compound A. For compound B, for carbon, we have 5. And then for proton, we have 1, 2, 3, 4, 5 as well. This tells us the number of unique carbons in the structure, or when we look into hydrogen, the number of unique sets or group of hydrogens. So based on that, since A and B has 5 peaks on the carbon, and in the formula you have 5 carbon, that means each of those carbon are quite unique. So what does this tell us? It tells us that the molecule is not symmetric. Because if it is symmetric, for example, you can relate the left side to the right side by a mirror, the number of peaks should have been lessened. Because the right side and the left side are now equivalent. But in this case, these are quite unique, so all 5 carbons have distinct peaks for both A and B. Now for the hydrogens, what I mentioned in the video lecture is that definitely the number of how the peaks are broken into or broken apart, or the number of coupling, tell us how many neighboring hydrogens there is. So for example, in this hydrogen spectrum, proton NMR spectrum, there are 3 information that we can gather. The first one is the position, this one, the ppm. So this is roughly at, say, 3.1, 2, 3, 4, 5. 3.4 ppm. This one is roughly at 2.8. And then this is 2.45. This one, 2.15. This one, the last one is at less than 2. So around maybe 1.8. Okay. The higher the ppm, the closer it is to the electronegative oxygen. So that's one clue. The second one is these numbers. The numbers on top refers to how many of such hydrogen gives the signal at say 3.4 ppm. Since 2H, this is referred to as the integrated value. So there are two hydrogens which appears at 3.4. Okay, so there's two hydrogen that appears at 2.45, three hydrogen that appears at 2.15, and then so on. So what you can do is compare those numbers and check in the molecular formula if it matches. If it matches. So 3 plus 2, 2 plus 1 would give you 3, plus 2, 5, plus another 3, so 8, and then 2. This gives 10. So in the formula, there's 10, so that means we already accounted for the 10 hydrogens. So this tell us that indeed same conclusion as what we have from the carbon-13, that the molecule is not really that symmetric. So because if it is symmetric, it might happen that although there's only 5 peaks, the number of hydrogens upon integration should match to that of the number of hydrogen. Okay. So for B, this is roughly around what is so 2 1 2 3 4 5 6 7 8. So this is 1 2 3 4 5. So roughly 3.55. Okay. These are just approximations. This is maybe around 2.80ish. This is around 2 point maybe 40ish, and then this is maybe 2.15 ppm, and then this is just slightly above 1, so 1 point maybe 2 or 3. These are very rough estimate. So number of hydrogens, the integration, ppm tells us how close it is from the O or the OH. And then lastly, the coupling, that's the number of how the huge peak is being broken apart. Okay. And that tells you the number of neighboring. So for A, this is a triplet. This is a singlet. This is a triplet. This is a singlet. This is 1, 2, 3, 4, 5. Quintet. So basta 5. Okay. 1, 2, 3, 4, 5. So roughly, this tells us in the spectrum of A that for the coupling, it's number of neighbor plus 1. So this tells us that The number of neighboring hydrogens for this peak is 2 because it's a triplet. This one is 0. This one is, but I'm gonna put this in a box because this is a little bit tricky. So this one is 2 as well. This one is 0. And this one is 4. For B, this one is a doublet. This one is a singlet, a doublet, a singlet, and 1, 2, 3, 4, 5, 6, a sextet. So number of neighboring would be 5, 0, but again, I'm gonna put this in a box. 1, and then 0, 1. So, the one that I put in the box, if you take a look and compare it with the other peaks, both for spectrum A and B, these are slightly broader than the singlet, say this singlet or this singlet. So the broadening of this accounts for that it is an exchangeable hydrogen. I mentioned in the video lecture that usually the hydroxyl hydrogen is not seen on the proton NMR because it is an exchangeable hydrogen. But in some instances, it can be seen, but it typically appears broader than usual. So, in this case, this peak in the rectangle or the box one is accounted for the OH. And okay, that's already for the OH. Next is considering the integration, the number of hydrogens. Okay. We use another color. This means this is a CH2. This is a CH2. This is a CH3 because there's 3 hydrogen. This is a CH2 because there's 2 hydrogen. If you're going to take a look into it, there's 5 set of hydrogens there is. While I already said that the C double bond O is for ketone here, we know that this is not an aldehyde because that if it is an aldehyde, it should have a hydrogen there. And that should appear in the proton NMR at really very high ppm, around maybe 9 or 10, which is not present in the spectrum. Okay. But I already mentioned that it is a ketone. So, there. How are we going to combine all those information for A? So, we already have a ketone. Okay, there you go. And we already have, it is a primary alcohol. So, we already have an OH. Okay. Now, what we need to consider is there's no other information given in the IR, in the carbon-13, and also with the degree of unsaturation. So there's no more double bond. These are just all CHs, or a normal carbon chain length. So how are we going to combine all those information? So we see here, based on the spectrum, that we have a CH3, this one, which is a singlet, so it doesn't have any neighboring carbon. So that means for the ketone, so it has only methyl group at one side. So because now this methyl group is attached to the carbon that doesn't have any available hydrogen for the hydrogens to couple. That's why we see it as a singlet. Okay. So we're already accounted for 2, technically 3 carbon. So I'm just going to 1, 2, and then 3. Now, let's just figure out if the remaining 2 carbons are are just in between these 2 groups here or not. Okay. So the way that we can figure it out, so there's 2 more carbon, right? So one possibility is two more carbon. So 2, 1, 2, 3, 4, 5. 5, yeah. Okay. If it just form just a CH, 1, 2, 3, 4, 5. Okay, 5 carbons. So a CH2 between the primary alcohol group and the ketone group. Or one, two, three, four. Yeah. 1, 2, 3, 1, 2, 1, 2, 3, 4, 5. Yeah, there. So now which of this? Both have a primary alcohol, but which do you think it will be? Let's check with the proton NMR. Okay. Now for the proton NMR, if we're going to check this one, so we already accounted for this. So this hydrogen is actually CH2, but this hydrogen is CH, and then this hydrogen is CH3. Now, if you notice, based on our accounting, there's no CH here. We have CH2, CH2, CH3, CH2. There are 3 CH2. So, we should be dubious about the right structure. But if we check the first one that I drawn, so we already accounted this. This is actually CH2. This is also CH2. And this is 3CH2. So it seems like we actually accounted the 3CH2. So this is more likely the structure. To further argue for this structure, let's try to assign the peaks. Hopefully, we're able to. So, if I'm going to number it, particularly the CH2s, because we're already okay with this. This is okay already. Okay. So, this CH2 is, say, peak 1. This is peak 2. And then this is peak 3. So, the CH2 at about 3.4 in terms of ppm, so that means it is at a higher ppm, so the closest to the OH, so this is actually the alpha, so that's 1. And to check, it is close to, sorry about that, it is close to a CH2 here, so that's why this is a doublet. Sorry, this is a triplet as indicated there. Now 2 is the one that is a triplet. Okay, it actually slightly higher ppm, so this would be 2. And these hydrogens will be 3. And it's quintet. So it's actually far from the OH and from the carbonyl. It is neighboring to 2 plus 2 hydrogen, so 4 plus 1. So that will give you a quintet in terms of multiplicity. So this is the primary, the structure of compound A. Now going with compound B and using the same process. Okay. Okay, so we have here 1 hydrogen, so this is a CH. This is 2 hydrogen, so this is a CH2. This is a CH3. And this is a 3 hydrogen, a CH3. A CH3. Okay. So what do we know so far is that, again, I mentioned that it is a ketone. So ketone, C double bond O, and it is a secondary alcohol, OH. Yeah. C double bond O and OH. I'll just use another color. Maybe this one. So a C double bond O and an OH, although I don't know yet how many carbons are there on the both sides of the OH and both sides of the C double bond O. Okay. But what we can learn from this, particularly the proton NMR, we have a CH, which is a sextet, meaning it is this one. It has a neighboring 5, which more likely be 1 CH3 and then 1 CH2. And since this is a CH, this part can be this. Let me draw that a little bit bigger. So we have a CH3 here, and this is the CH that I'm referring to, and then it also has a CH2. That means this should not be, that connectivity should no longer be a carbon chain length with carbon and hydrogen, because that means we're no longer going to satisfy the multiplicity. So more likely, it cannot be the C double bond O. More likely, that will be the hydroxyl group. So with that, so this is the CH3. This is the CH. Okay. This is the CH, and this is the CH2. Okay. I don't know yet what's going to be the connectivity of that. But thus far, we already account how many carbon? One, two, three. Sorry. Same. I'm just referring to the same carbon. About 2 and 3. Okay. This is the this is supposed to be the 3. Okay. So 1, 2, 3, and that of the ketone, 4. So we already accounted 4 carbons. Only 1 carbon is remaining because we have a C5 compound. Okay. So how are we going to take a look into it? So far, we have a CH3, a CH, and a CH2. This is the CH. There are 2 CH3 here. This is the CH2. There are 2 CH3, but if we check the multiplicity, this is a singlet, this is a doublet. So more likely, this one is attached to or close to the carbon that bears no oxygen. Bears no hydrogen. So that means this carbon. Okay. So therefore, if we combine these two, the structure would be the structure would be 1, 2, 3, 5. This would be the double bond. This will be the OH. Okay. This one. 1, 2, 3, 4, 5. Now, if we're going to account for the carbon, for the proton, this would be, I'm just going to write 1, 2, 3 as well. 1. This is clear. This is OH. 2, 3, 4. So 1 is this one, the hydrogen from that carbon, closest, or the alpha hydrogens. 2, a CH2 that is slightly higher ppm. Okay, well, there's only one CH2 anyway, so this is 2. And then we have the 2 CH3. This is the one that is on the other side of the ketone. So this is 3, and therefore this is 4. So this is the structure of compound 4. Compound B. So the first one is the primary alcohol, the second one is a secondary alcohol. And both of them actually have the ketone group on the second carbon. Well, it's second carbon if we're counting with respect to the ketone group. Alright, so moving on. For problem 7, we have a series of transformation. So either give the identity of the reagent or the major organic product in the synthesis scheme presented below. Okay. So the first one, we react it with POCl3 with pyridine. We know that this is dehydration, and in dehydration, this will still consider side chef rules. Now, going from alkene to alcohol, B, and this is Markovnikov reaction. We're adding the alcohol on the more substituted carbon. So B would be, so we're actually looking into oxymercuration, demercuration, followed. So the first one will be mercuric acetate in water with THF, and then next one is sodium borohydride. Okay, we get to this. Okay. Now, going from this alcohol to the alkene presented over here, okay, that's going to be a little bit tricky. So now let's just move backwards. So this alcohol with bromine, so that's a halohydrine. Starting off from this alcohol, we know that that's going to be halohydrine formation, where the OH will be added onto the more substituted carbon. So the reagent here will just be bromine water, since this is halohydrine formation. Now, for this, going from the alcohol to the alkene, this is a little bit tricky because what we know so far is if this will be dehydrated, it will follow the side chef rules, wherein you're generating the more substituted alkene. Okay. I'm not certain if you had tackled this from Chem 43, but there's another elimination product possible, and this is the Hoffman elimination product, which actually consider the opposite of side chef, which is the least substituted alkene. And one way to generate this from alkyl halide is, first, if you have a bulky alkyl halide plus a bulky base. Okay. So a bulky alkyl halide and a bulky base. So you'll generate the Hoffman degradation. Okay. How do we know that this is a Hoffman degradation? Because we see that the double bond is actually exocyclic. Because it's going to be a side chef product, it's going to be always A, because that's resulting to a more substituted alkene. So if we're going to follow this description, we need to have a bulky Rx, and the bulky Rx is actually a tertiary. So convert that to a tertiary Rx. So D, let's say a bromine, this is a bulky Rx. So it's a tertiary alkyl halide. Alkyl halide. And then, the way to convert it to the least substituted alkene is by using a bulky base. And one of the bulky base that is typically used is the tert butoxide. So CH3O minus with tert butyl alcohol, or you can just simply say the tert butoxide, and it will generate the Hoffman elimination product. Another typical bulky base that is used is the one referred to as LDA, which is a lithium diisopropyl amide, which has this structure. Those are lone pairs. Okay, that's diisopropyl bromide. This is actually negatively charged. So, or the potassium tert butoxide, or the butoxide here. If you want, put potassium there. So, with that, how are we going to convert this alcohol to this alkyl halide or alkyl bromide? So that is just an SN1 reaction. So what we do is just simply use an acid. So this is the scheme that will convert the given alcohol to the halo or the bromo hydrate. Now this will be the last slide. And this is providing mechanism or arrow pushing that will account for the transformation below from an alcohol to an alkene. So this is a dehydration reaction, and what we know is definitely in the presence of a an acid, the OH group will be converted to the better living group, water. So let me just draw out here O3. Okay. So we have lone pair here. So the hydroxyl oxygen will abstract a proton. Okay, so this will give you essentially OS H minus plus this compound or species, and then this will be cleaved to lose water, so it's called dehydration. So you'll be generating the carbocation, and this is a secondary carbocation, but if it does a metal shift, sorry, there should be a metal group there. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. Okay, so there should be a metal group there. So if it does a metal shift, you'll generate to a tertiary. So this is secondary carbocation, tertiary carbocation, which is more stable. Okay. So from here, you can have, these are beta hydrogens, okay. But obviously this is the more favored beta hydrogen to be abstracted as proton, because it will give you a more substituted alkene. So and you will generate the alkene over here. Please don't forget to draw out the metal group there. Alright, so that's for the mechanism. And that's all for now. Thank you very much.